Now that we've talked about finding the arc length of a curve, let's talk about taking a curve, creating a surface of revolution by revolving that curve around a given axis, and then considering the surface area. And actually what we're going to be looking at is just the lateral surface area. So we're not going to be considering these ends. This solid obviously has some ends to it, just the lateral surface area. So the surface area of the body of the solid that we're looking at. So we're going to calculate that lateral surface area right there. That's what we're going to look at. Now for this one, what we're going to do, I'm going to just verbally talk through it, and then we're going to jump right into the formulas and compute some actual surface areas on this video. But the idea is we're going to take a little segment, just like we did for arc length. We're going to revolve it around, and when we do that, when we revolve that little segment around, what we get is a band. We get a little band here, and we're going to compute the surface area of that band. Now that band goes around the back side too. So we're going to compute the surface area of that band. We're going to add up all the bands. We're going to create a bunch of bands, add them all up, n bands, let the number of those bands go to infinity, and that will, of course, create an integral formula that we can work with. So that's the idea. We're going to break up that surface of revolution into a bunch of little bands of surface area, compute the surface area of each of those bands, add them all up for that total surface area, and let the number of bands go to infinity. Let n go to infinity, which will create that Riemann sum for us. So I'm going to skip over all the derivation of that, and we're going to jump straight into the formula. It has some similarities with our arc length formula, which is nice. So here is our formula for the surface area of a surface that is found by rotating a function y equals f of x, where f of x is positive and has a continuous derivative from a to b about the x-axis. So this is for a region that we've taken, bounded in the xy coordinate plane, and we've revolved it about the x-axis. So turns out the surface area formula, and you can see the derivation in the book if you want to read through that derivation. As I said, we take those bands, revolve them, we take a little line segment, revolve it around the axis of revolution, creating a band that we can compute the surface area for using some geometric formulas, and then add up all those bands. We end up with 2 pi times f of x times the square root of 1 plus f prime of x squared dx. Now, as a little note, I mentioned this has some similarities to the surface area formula. And notice, or sorry, the arc length formula. The surface area formula has some similarities to the arc length. And notice our little arc length formula here. Remember, to calculate the arc length, we took the integral of the square root of 1 plus the derivative of the function squared. So you can see some similarities right there. In fact, what we can see here, I wrote it in both ways actually. So I wrote this with f of x and y, and as well as I used the prime notation and the Leibniz notation. So just writing it in two different forms so you can see both of those formulas. And let's consider just the case where we have x as a function of y and we revolve rather than revolving around the x-axis. What if we revolved about the y-axis? So if we're revolving around the y-axis, our formula is 2 pi g of y times the square root of 1 plus g prime of y squared. Notice that similarity to the arc length formula again right there. And we could also write that, remember that g of y is x, so we could also write that as 2 pi times x, trying to get rid of that highlight, 2 pi times x times the square root of 1 plus, and again, notice I use Leibniz notation, dx, the derivative of x with respect to y, since we're integrating with respect to y here. And so those are our two surface area formulas for a surface of revolution. And we have a little bit of shorthand notation. I want to just scroll down and look at a little bit of shorthand notation and talk about where the shorthand notation comes from, because sometimes I do like to utilize the shorthand notation. So if we uses the shorthand notation that ds squared is the differential dy squared plus the differential dx squared. And if we think about that, if we're taking a little band and we think of that little band right there and revolving it about, this is how we're creating this surface area again, remember, revolving it about the x-axis. Now remember that length right there, I covered it up when I was drawing that, but that length from the x-axis to the surface of revolution, that length right there is the y. And it turns out that the circumference of that band, and I gave it some width right here just so that you could see it, because we're talking about surface area, but again, remember, we're letting that width get infinitely small, and so the circumference of that band is 2 pi times y, and the thickness of that band we think of as ds. And so what we got are the width of the band. So that's our width, and y is our radius of the band. And so what you see here is when we're rotating around the x-axis that this surface area formula is actually a circumference times a width of the band. And you can see I wrote that out in words up above. It's the circumference times the width of the band, and that's where we get that 2 pi y ds. And now we remember that with ds, if we're thinking of that shorthand notation from above, if we solve for ds, if we take the square root of ds and do a little bit of algebra, ds can be written in either of the two forms I have written here, depending on which axis of revolution we're using, an x-axis or a y-axis of revolution. So are we going to integrate with respect to x or with respect to y? And so you can see that same exact formula, but instead of the circumference being 2 pi y, it's 2 pi x, because this radius right here to the band is x when we're going around the y-axis. And then we get that same circumference times the width of the band of the surface, and we get 2 pi x ds instead of 2 pi y ds. And again, we can use our ds notation from either of those two. So it's just a shorthand notation. It gives us a way to think of it geometrically. We're taking the surface area of those bands, and we can utilize this formula, or this sort of shorthand way to remember the formula, I should say, for surface area. Okay, let's jump into a couple examples. All right, so for this first example, if we want to find the surface area of a solid that is formed when we take the square root function, y equals 8 times the square root of x, and we revolve it about the x-axis from x equals 9 to 20. So I did a little prep work. I actually drew, this was one we could easily draw. It's a square root function, so it has that kind of general swooping shape. And we took it, we revolved it about the x-axis, and we created a solid of revolution that I have sketched here. And if we want the surface area of that solid, since we're going around the x-axis, we're going to be using our surface area formula for going around the x-axis. So which is going to be 2 pi y, the circumference. And again, you can think of taking a little band. If we took a band and we revolved it about, and we wanted the surface area of that band, 2 pi, we take the circumference times the width of the band. So the width of the band is the ds, and the circumference is going to be 2 pi times the radius, and the radius of this band, because this height right here, this radius is y, is going to be 2 pi y ds. So that's one way to remember it, and then we use our ds is coming out of that arc length formula. We've got that square root of 1 plus f prime of x squared, or dy dx squared. Okay, so just that's our formula. Now we got to do that, right? We got to take the derivative, we got to square it, add 1, take the square root, pop it into that formula. So that piece, as I did with arc length, I like to do the simplification of that piece off to the side. So since y is equal to 8 square root of x, or 8x to the 1/2, I'm going to take the derivative, so dy dx, and that's going to be 4x to the minus 1/2, which is 4 over x to the 1/2. And then I'm going to go ahead and take the square root of 1 plus dy dx squared, the derivative squared. You could write f prime of x there too, but I was calling it y since that's how it was defined and using Leibniz notation. We're going to take 1 plus 4 over x to the 1/2, and we're going to square it. And that's going to give us the square root of 1 plus 16 over x. I'm going to go ahead and find a common denominator there. We've got x. That's going to be the square root of x plus 16, big square root actually, all over x. And that's what I'm going to pop into my surface area formula. So my surface area formula is going to become the integral from x equals 9 to 20 of 2 pi times f of x, which was 8 square root of x, times the square root, since I've already done the simplification, of x plus 16 over x. And we're integrating with respect to x. Now I'm going to zoom in on that a little bit just because I want to simplify and do that integral now. And so as we're simplifying, here I notice a couple of things. One, I'm going to go ahead and pull out the 16. I got a 16 pi. I'm going to pull that to the front. So 16 pi to the front. I'm integrating from x equals 9 to x equals 20. I've got the square root of x left, and I'm going to separate this because I notice on that, this is a big square root. I'm going to square root the numerator and the denominator because I notice that the denominator is a square root of x, and I have a square root of x right there, so I can reduce those. This is all being integrated with respect to x, and now I end up with just the square root, the integral of the square root of x plus 16. So before I go to my next line, I notice here that I'm going to need to make a little substitution. So let's let u equal x plus 16. Then the derivative du dx is just 1. Separate that differential for the substitution, so that's just 1 times dx, or du is equal to dx. So now I'm integrating simply u to the 1/2 power with respect to u. Now I'm also going to go ahead and switch my bounds. So x was equal to 9. So that means u is 9 plus 16, so that's 25. And u is 20, and the upper bound becomes 20 plus 16, which is 36. So now I don't have to go back in terms of x in the end. So this ends up becoming 16 pi, and then the integral of u to the 1/2 is u to the 3/2. We're dividing by 2/3. I'm sorry, dividing by 3/2, which is the same as multiplying by 2/3. And we've got from u equals 25 to 36. All right. And now we end up with, nope, nothing reduces there. So this is 32 pi over 3. And then we're going to plug in the 36. So 36 to the 3/2 minus 25 to the 3/2. Those are perfect squares, the 36 and the 25, which was very convenient. So this becomes 32 pi to the third, and then we take the square root of 36, which is 6. So 6 cubed minus 5 cubed. So we end up with 32 pi over 3 to 16 minus 1, 25. And that ends up giving me 91. So 32 pi over 3 times a 91. And that, I'm going to grab my calculator real quick, is 2,912 pi over 3. And that is in units squared of surface area. And there is how we can calculate the surface area for a solid of revolution. So we utilize that formula. Get it all on the screen here. Utilize that formula. I like to do the simplification off to the side first. Utilize the formula and then integrate. All right, let's do one more example before we wrap this video. So let's find the surface area of a solid formed when we take x equals the square root 12y minus y squared, and we revolve it about the y-axis. So this one is not one that I would expect you to know how to graph. We could go to Desmos and see what that graph looks like if we wanted to. I'm going to skip that part and just jump right into the calculation because we're going around the y-axis. We know the bounds from 2 to 10. And we just need to plug this into the formula for revolving about the y-axis. So when we go about the y-axis, 2 pi x ds, where ds is that square root of 1 plus what's either going to be dx dy squared with respect to y, or dy dx squared with respect to x. Or you could use the prime notation. So just like before, I like to do my little side work over here. So let's do some side work before we pop this into the integral. So we've got x equals the square root, I'm going to write that as 12y minus y squared to the 1/2 since I need to take the derivative. So then dx dy is going to be 1/2 12y minus y squared to the minus 1/2 times 12 minus 2y. And then here, I'm going to continue to simplify this. Notice the 1/2 and the 12 minus 2y. We can distribute that 1/2 to those two terms. So this becomes 6 minus y over, now in the bottom, we end up with 12y minus y squared under a square root. It was to the 1/2 power when I dropped it down, but I changed it into a square root. Okay, so all of that. Now we need to pop that guy into our square root of 1 plus dx dy quantity squared. So let's get this algebra and get it simplified. This is 1 plus, we're going to square 6 minus y over the square root of 12y minus y squared. So when I square that, let's move this up to the top of the screen. When I square that, I'm going to get 1 plus, I'm going to get the quantity 6 minus y squared. And in the bottom, 12y minus y squared, because the square root is going to be squared. All right. Now let's find a common denominator. So let's multiply this guy by 12y minus y squared, 12y minus y squared to find a common denominator. And we're going to end up with 12y minus y squared plus. Now, you know what else I'm going to do? I'm going to expand this out in the numerator. So we know in the denominator that we have 12y minus y squared, but I want to get this as simplified as I can. I want to simplify this square root as much as possible before I pop it back into the integral. So I'm going to expand that numerator. So that's 36 minus 12y plus y squared. Now I'm looking at this problem and I'm thinking, this was cooked up really nicely, because check it out. These y squareds are going to cancel. These 12y's are going to cancel, leaving me with just a 36 in the numerator. And it's over 12y minus y squared. I lost the y when I said it, but I didn't write it. 12y minus y squared. And that, of course, is just 6 over the square root of 12y minus y squared. So look at that. That simplified really nicely. And now I can pop that into my surface area integral. So our surface area, we're going to integrate across the bounds from 2 to 10. It's going to be 2 pi times x. Well, x was that function, the square root of 12y minus y squared. And we're going to be multiplying by what I just found right here. Remember, that was my simplification for that square root. So this is going to be 6 over the square root of 12y minus y squared, all with respect to y. And oh my goodness, look at how convenient that is. We did that simplification so it makes this particular step really nice, because you can see right away, boom, boom, those two square roots cancel. And look at this, what appeared to be a fairly complicated integral at the start ends up being just the integral from 2 to 10 of 2 pi. It's actually 2 pi times 6, so 12 pi dy. And the integral of 12 pi is just 12 pi times y, because that's just a constant, evaluated from 2 to 10, and that's just 12 pi times 10 minus 2. And we end up with 12 pi times 8, and that is 96 pi units squared of surface area. And that one, even though in the first couple of steps, sometimes when we're doing these problems in the first couple of steps, right, when you have to take a derivative, square it, add 1, take the square root, there can be some simplification, which is once again why I like to do this off to the side, do a little bit of side work, get that as simplified as possible, because a lot of times there's some algebra to work through there, and we want to be careful with our algebra and do it correctly so that when we pop it into the integral, we're able to integrate without having to do a lot of simplification. So that's why I do that. Maybe I'll try to zoom in as much as I can on that. I know that got really small as I finished it out. But that's how we're going to do our surface area problems. So I want to add one little note here at the end. Let me go back to our formulas. I'll add one more note here at the end. So here's the surface area formula projected on the screen in the start of that first example. This is revolving about the x-axis, and then of course here is revolving around the y-axis, a similar formula but a different orientation. I want to mention with these particular problems, we are a little limited in the type of surfaces we can actually compute the surface area for right now because we haven't done all of our integration strategies. So we will see some of these same type problems, some of these surface area problems as we go through chapter 8 and get a few more integration techniques under our belt, because unless these problems are cooked up really nicely, like the two I just did, where the simplification works out and we're able to either use a simple integration strategy like substitution, which is what we did right here, or it's cooked up so nicely that when we do all of our side work and we pop it back in, we end up with a very simple integral that we can integrate just using basic integration strategies. Unless the problems work out that way, we are limited in what we know how to integrate right now. But caveat, star, put a little star on that statement because we are about to start chapter 8, and chapter 8 is really going to open the door to all types of functions that we're going to be able to integrate. So we will see more applications, more volumes, arc lengths, surface areas, and simple areas in chapter 8 as we get more ability to integrate more techniques and the ability to integrate more functions.